We'll be talking today about microservices, which I'm sure you guys have heard of before. The only tricky part is going to be that I just came in from the airport after a 34-hour travel to get here. So it's possible some of this stuff won't make any sense. If you come afterward, I'll be around for a little bit afterward. Please wake me up and ask questions if I said something that doesn't make any sense. But we'll be talking about some of the patterns that emerge when you start to go down the path of doing a services architecture, microservices architecture. How many people in here are doing or think they're doing microservices? If you could raise your hand. Oh, that's a good number. Awesome. How many people think that doing microservices is easy? One back there? I don't know if you're doing microservices there, but all right. So my name is Christian Posta. I'm based in the United States, and I travel and meet with a lot of our customers at Red Hat, so I work at Red Hat, and I help them understand what this cloud, DevOps, microservices stuff really means to them. I got the opportunity about 6 years ago now, 6 or 7, six, to work with a cloud company, one that is kind of heralded as the microservices poster child. And they had very mature automation, and they followed that's where the phrase two-pizza team came from. And so I got to work very closely with a SOA or microservices type environment and that culture that exists around it. And I try to help our enterprise customers who are coming from a place that did not resemble that, how they get to that new way of doing things. I speak at conferences like this one. I'm very happy to be here. And I write on my blog quite frequently, and recently just published a new book. Well, the one up here actually we published a couple years ago, but the one that we just published a month ago called Introducing Istio Service Mesh, you can get the electronic copy on developers.redhat.com. All right, so let's get going. Let's start talking about. We're going to set a little bit of context. This part, the next handful of slides here, this is an entire talk on its own. But what our organizations, the organizations that I meet with, are struggling with is how they keep pace with the market. How do they, these small startups that are coming up and they're disrupting not just them but the entire market that they play in. They need to learn, or they had to figure out how to innovate within these organizations that have been around for many decades and have built very successful products, but they're not used to innovating. And so there's a lot of stuff that goes into that, but one really important and fundamental piece is that innovation is admitting that you don't have all the answers. You don't know what the next steps are going to be. The market dynamics, competition, you can't predict. Things are too complex. You can't predict what the next steps are going to be. Now, what we need to do is build an engine that's capable of figuring out what are the right questions to ask. So what this means is even our customers don't or might not know what delivers value to them until you put stuff out in front of them, until you ask questions about whether or not this really works. Now, in this unknown, highly unknown, very complex world, do we have a method or an approach for dealing with this, for understanding how to deliver value in this environment? And for those of you who come from a science background, you may be familiar with the scientific method, which is exactly built to explain or understand the direction to go and solve for these types of problems when the problem space is completely unknown. So we start by making observations, coming up with ideas, hypotheses that we think might work, and we test those. So translated over to what we do in business, we don't know exactly what the next step should be, but we're going to put things out in front of customers and we're going to evaluate their response. Now that's a little different than the way IT works today, because IT is really, they've grown from a background of optimizing the business and reducing cost inefficiencies and so on. So they've really been told, hey, you need to do this. These are the requirements for this. And if you look at the pattern here as a whatever, I want this goal so that I can receive this benefit. That's pretty a definite statement. But in reality, just because you come, you have a project and you finish the project on time, and maybe even under budget, that doesn't mean it necessarily delivers the value originally intended, right? So if we start looking at this instead of requirements as hypotheses, and again, I stress I'm just touching a very high level here. This actually permeates the core of how you build the team structures and culture and so on. But instead of treating these as requirements where we know if we follow through we're going to get the end result, which, like I was just saying, you can't predict that for sure 100%. If we treat these as questions, as hypotheses, then we can move, start to learn about what will deliver customer value and start to move in the right direction through this mode of working. Now, translated to IT, what this means is we need to get smaller chunks of software out faster, get those in front of our customers, and use telemetry and feedback mechanisms to understand whether or not that had the impact that it had intended. Microsoft did a study about 8 years ago, and it was a study, what were the actual outcomes for a lot of the good ideas that people had in the company, executives, architects, and so on. They came up, they go to get budget and fund these projects, and they come up with these good ideas and see whether or not, Microsoft did a study to measure whether or not they achieved those outcomes. 30% of the time for these good ideas, they had a negative impact, negative outcome. Another 30 to 35% of the time, it had zero impact. So, and then the rest, there was positive impact. But so I guess what I'm saying is if you start to work in this way, you can reduce the waste. So you can ask questions, get code changes out in front of customers, evaluate what that response is, and eliminate the waste of going in the wrong direction. Now, to do this, we need to rethink how we look at our tools. We need cloud platforms to enable self-service for teams, and we need to build resiliency into these things because cloud platforms, by definition, are not going to be resilient. But cloud native in general describes this way of working where we're hypothesizing, constantly putting out new ideas and evaluating whether or not they deliver value, and doing this economically. Because if the cost is too high to run these experiments, we're going to run fewer of them, right? We're going to try to batch them up into smaller or into bigger batches and do them fewer times. I used to also work at a big bank where we deployed code once every quarter. And you can imagine the amount that you can learn by jamming everything into one single deployable and putting that out there and learning 4 times a year versus maybe deploying once a day, or Amazon's however many tens of thousands of times a day that they're deploying. And that's important because having that IT platform or that cloud platform and that way of working and making it economical is a foundation for driving high performance in our IT teams. And if you've seen any of the State of the DevOps reports from IT Revolution and Puppet Labs, Gene Kim and those folks, they've shown that high-performing IT organizations that can run like this have a demonstrable impact on business value and market share and so on. Now, they describe high-performing teams as being able to deploy very quickly and deploy many, many times a day or week. And in this case, I think this is the 2015 State of the DevOps report, where we see that the delta, the difference between the high-performing teams and the low-performing teams is the ability to get deployments out 30 times more quickly. 30 times more deployments. The deployment lead time 200 times more quickly. So code gets checked into their source code repository and can get to production 200 times faster. In 2016, or this is the 17 report, I think. In the 2017 report, you'll notice here, and I'll turn for a second, that the 2016 numbers were 200x more frequent, and in 2017, only 46x more frequent. Same thing with the developer lead time. 2,500 times faster, and then in 2017 that went down actually. What they found was that teams are starting to go down the path of maturing their capabilities around delivering software. So using containers, using CI/CD, these types of automation practices they put in place to be able to get things out and kind of close the gap. It's still a decent sized gap, but they've been able to close it a little bit. Now, what you notice down here, they were in 2016 able to go 24 times faster for mean time to recovery. That gap has increased in 2017. Same thing with change failure rate. The number of deployments that cause failure was 3x lower, and now it's 5x lower. So what we're seeing is, although folks are going down a path to be able to deliver more quickly, they're introducing more problems. They're introducing more issues into production, and they're not well equipped to recover from that. Now, with any new methodology like microservices or whatever, we expect that there's going to be challenges in the way we work, that we actually try to implement this. Now, when you start to say, well, you need to deploy faster, you need to learn from these deployments, oh, but now you're introducing all of these bugs. What can we do better to improve that? Then you're probably going to ask, well, how hard can it be, right? We're already moving to REST services, maybe gRPC. These services are communicating. They're loosely coupled. We followed all of the guidelines that we're supposed to, have higher quality code and deployment confidence and so on. But how hard can this be? When services start to talk to each other, that's where the complexity comes in. When A talks to B, it doesn't really talk to B nice and neatly like this, right? It goes over network, and it is an asynchronous network. There's no predictability about how long the calls between the services will take. And it could take multiple hops. And things could start breaking anywhere in between A and B. Now, things could get too slow in the network. Things could actually, your request could actually make it over to B. B could do some processing, and then maybe B fails, or maybe the network on the way back fails. There's a lot of unpredictability in the network as services start to talk with each other. And if we move to a microservice style architecture, you're going to have more of this. And if you, moreover, move to a cloud environment, you're talking on even more unreliable networking infrastructure. So we see failures and slowness and so on. But as we start to move to this type of architecture, we're pushing a lot of complexity that we took for granted. We had a lot of assumptions when we built our monolithic applications, right? We could talk to a database and get atomicity, so no weird partial failure problems. Now we can see that. When we talk to the monolith, calls are incredibly fast because they're in memory, and they will always succeed or fail. In the network, they could just hang and not do anything. So we start to see a lot of this complexity pushed between our services that we could, in the past, kind of just assume that we don't have to deal with that. Now we have to deal with that. Developers, as we build services, have to deal with this complexity. And as we make more deployments and make more changes to our system, it just compounds this problem. So what are these problems? What are these challenges that we're talking about? So as services come and go, topology changes, we need to be able to discover them dynamically at runtime. So we need service discovery. When calls fail, we might want to introduce retries to the calls and so on. So timeouts, load balancing, rate limiting, circuit breaking, these type of resilience patterns that we expect now our applications or our services to be aware of and to implement. Routing between services, deadlines when things no longer need to complete, outlier detection, health checking, traffic shaping, all of these things. A/B rollout, fine-grained control of request routing, fault injection, logging, metrics, all of this stuff. Now we're expecting developers are going to have to do all this stuff in their applications. But I left one thing out. Did anyone notice in this list that I left one thing out? Yell it out if you know. Yeah. So this is another big important facet to our services architecture, is now we're increasing the opportunity for vulnerabilities. We're increasing our attack surface. Everything's going over the network. Now we have to think about what does that imply in our services architecture, and how are the applications, how are the services, or how is the infrastructure going to deal with that? Now, luckily enough, Netflix had to go down this path, and in 2009, 2010, they started building libraries for developers to consume to be able to solve for some of these problems that we saw. And so they built libraries like Netflix Hystrix, which is a circuit breaker implementation, Netflix Zool, which is an edge router, kind of a load balancer and router functionality, client-side service discovery, and client-side load balancing. So we don't centralize load balancing and service discovery into a central gateway or central proxy. That can be a limitation or bottleneck. Tracing and service registries and all. So they built a lot of this stuff. And in their world, they had to, right? Because they were going to AWS, they were going cloud native. The stuff didn't exist, and they needed to solve for these problems. What they ended up doing with these libraries, each developer, each development team would bake them into their applications. So how many people in this room have either seen or used Netflix OSS? Decent number. It was a Java conference. So all these frameworks were built and targeted for the JVM. And in their applications, you wanted circuit breaking, you would pull in the Netflix Hystrix, all of its dependencies, Ribbon, and for client-side load balancing, all this stuff. And these would live with the application, in the application code, in the namespace of that application. But there are some drawbacks to that approach, right? So if you're building all these libraries, like Netflix did, and you're targeting a specific programming language, you're kind of forcing developers to use that language if they want to participate and build services for that ecosystem. But a single language doesn't fit all use cases, right? So you might want to use the JVM and Java for a particular application. And I know there's a Java conference, but don't hate me. There's real reasons to use Golang or JavaScript or other programming languages as well. But when you start to do that, how do you bring that in and operationalize that? How are you certain that the implementation in Golang for circuit breaking is operating exactly the same way as the implementation for Java? You know, your developers might go off and look at the NPM listing and find a Hystrix.js or whatever they pull down, or maybe they write their own, and you get a lot of inconsistency in how these different concerns are being addressed and how they're being implemented. You know, how you do patching and upgrading of these libraries, if they're in the code, becomes a little trickier, a little harder. Now, as Java developers, we have options, right? And then that's good. Now, the Spring folks, they built Spring Cloud Netflix on top of the Netflix OSS stack. And so you can bring in all of these different dependencies to do that if you're doing Java. If you're doing Java with Vertex, there are similar options to bring in some of those libraries to provide that functionality. But like I said, maybe you want to do reactive on the edge for web gateways and web APIs, so you want to use Node.js. But maybe you saw Golang come along and it's really fast and compiles down into a single binary, so let's use that for some services. But Python's actually pretty easy to read and nice on the eyes. Maybe we want to use Python. And believe it or not, people still use Perl as well. And if you end up with all these different permutations of languages and cobble together libraries and frameworks for trying to implement resiliency and routing and security and these types of things, and you try to operate this at scale in a cloud environment, you end up with a gigantic mess. And this becomes intractable, right? This is not sustainable. But what if we could abstract this functionality to a single binary and apply it to all services consistently? So it doesn't matter if we're using Node.js or Java or Python or whatever, we can get the same behavior out of our service discovery, client-side load balancing, circuit breaking, retries, timeouts implementation that we would expect. And we don't, just like, how many people, I'm just curious, how many people in here use Kubernetes to deploy their applications? Oh, that's a decent number. Okay. Kubernetes did something interesting, kind of like this, in the same spirit. So Kubernetes is a deployment platform where you deploy your applications, but they did put in some rudimentary ability for the applications to talk to each other and find each other at runtime. So they have a concept called Kubernetes Service, which provides a virtual IP that at runtime can actually load balance and find services. And what's interesting about that implementation is, since it was just a virtual IP, you could use DNS inside of Kubernetes to do service discovery and basic load balancing. And that's pretty awesome, because even if you're running in Kubernetes today, then you don't need special libraries for service discovery and service registries like Eureka and all that stuff. You can just use DNS inside of Kubernetes. Pretty simple. Any language can do that. So they started to push some of that functionality out of the application. And that's the direction that I'm talking about when we say, well, what if we had a separate service or a separate abstraction that could do that for us and push that out of the application so that we can get this consistent behavior? What if our services could just talk to an intermediary that can apply or enrich any calls that go through this intermediary with this behavior, with this functionality? So the service talks with the proxy, and this proxy will then send the traffic outward, but it can do things like retries or timeouts, or circuit breaking, these types of things. Just kind of curious, how many people in the room have heard of Envoy? Awesome, cool. That's good to see. So Envoy is the little binary, the little proxy that enriches service calls with that behavior. It is written in C++ on purpose. So there's another thing that kind of differentiates Envoy from some of the other implementations. It's written on C++ to be a little bit more deterministic at high load and at those higher tail latencies. We don't want random garbage collections happening at that level. It is at its core a byte processing filter, L3, L4. So if you're familiar with the networking stack terminology, but has a lot of out-of-the-box application level, L7 level filters that understand application level requests and messages. So for example, it has HTTP1 and HTTP2 filters. So it understands the requests that are going over the proxy. And since it can understand that level, it can do interesting things like do retries or timeouts on these requests. It can do things like advanced load balancing, and so zone aware, like if you're in different fault zones or availability zones, zone aware load balancing. It also, since the requests are going through this proxy, it can keep telemetry and statistics about what's happening with the requests, how long they're taking, how many circuit breaking events have happened, and so on. So this little proxy through which our applications now talk to the outside world, that's where Envoy fits. So Envoy is a proxy that implements these types of concerns: so circuit breaking, outlier detection, retries, timeouts, rate limiting, traffic shadowing, all these things that we started to enumerate in the previous slides. Now if you start to look at this architecture and start to say, well, this proxy thing kind of feels like a part of the application, right? It's not actually deployed in the application, it's separate, it's outside, but it is kind of part of the application. And in the Kubernetes world, since we have a unique or kind of nice ability to co-deploy components that need to be deployed atomically together. That term's a pod, a Kubernetes pod. We can implement interesting deployment patterns like Sidecar Patterns or Ambassador Patterns or some of these different ones. And the term we use with Envoy is the sidecar. We put this little shot of whiskey right next to the beer, and they kind of go together, right? Especially if you're at the airport like I was. Now, this ability of, or this term sidecar or service proxy or whatever you want to call it means that that for each instance of our application, think each JVM, each Tomcat or Spring Boot instance or whatever, we have this separate proxy that implements these different behaviors. In a little more detail, basically the application here enumerated as downstream talks to the outside world by talking to Envoy, and it may or may not know that Envoy's there. That's another key point. That the downstream could talk to, let's say, localhost : I don't know, 9001, and maybe it knows that Envoy's there. And if it talks to localhost 9001, it knows Envoy's there, and then Envoy will do the routing and all that stuff as it talks upstream. But it could also just say, I'm going to talk to foo.service.com, and it thinks it's talking directly to foo.service.com, but we can intercept that traffic and route it all through Envoy using something like IP tables or something. All right, so the application doesn't have to know that the proxy is there, but it could. There are some implementations where it does. So if you end up with something like this, where all the different instances have this proxy and now have all this capability that application developers don't have to kind of throw into their class paths and into their applications, we start to build a mesh, right? So all these applications are talking to each other through these proxies. And it's kind of where the service mesh term came from. Who's heard of service mesh? Just curious, raise your hands if you could. Okay. A service mesh is the ability to solve for those challenges we saw earlier as an infrastructure service, decentralized infrastructure service that applications can rely on, and solve for things like resiliency. So some of the things that I've been harping on are resiliency. That affects developers because that's the stuff that you're baking into your code quite a bit. Security, and we'll talk about that. Observability, so as the requests are going back and forth through these proxies, we can see what, we can capture telemetry, we can capture traces, so distributed traces like open tracing. The proxies can handle doing that for us. So we get a little better understanding at runtime of what's really happening in our cluster, and routing control. So one of the things that I was pointing out earlier, when we saw the gap kind of shrink between doing the number of deployments or the deployment time, but we saw the gap increase for mean time to recovery or change failure rate. With a service mesh, we can have a little more control over what's a deployment and what's a release. And using this routing control, we can say, we can separate those two out and say that a deployment is getting our code into production, but that doesn't mean it takes traffic. We can put it into production, run smoke tests, see how it interacts with the other components, but graduate the release. So actually, once we start doing the release, we can start to bring real traffic to the deployment. So we can maybe start off with non-paying customers or internal customers and say they always hit this new deployment. So we'll start to release it. And then slowly graduate that out to, well, maybe we'll do this region of customers, maybe we'll do the gold level customers next, platinum or whatever. So we have a lot more control instead of just big bang, here's a brand new piece of software and it doesn't work, well, all hands on deck and everybody stay overnight, right? So Service Mesh provides a lot of control when doing those deployments and releases so that you can drive down your change failure rates, right? And you can increase your, or drive down your mean time to recovery. So all the traffic flowing between our applications flows through these proxies, and the proxies deal with requests and messages, HTTP requests, but there's also MongoDB filters. There's folks working on a Kafka filter. There's folks working on AMQP filters. So the proxies are going to, over time, start to become smarter and smaller, understand these application level constructs even more. And we term this the data plane. So all the messages and requests are flowing through the mesh and through this data plane. But we need something to be able to make some sense of a large cluster of these proxies. We don't want to go in there and individually configure them and manage them. And so that's where a project called Istio comes into the picture. How many people have heard of Istio? Raise your hands if you could. Awesome. So Istio is an open source project that is an implementation of a service mesh, but it has both the data plane, so the proxy piece, and the control plane, which is how we manage and configure the data plane and tell it what to do and what we expect. So in this model, the functionality that we're looking for isn't baked into the application. It is out of process, but it is deployed alongside the application. And so that makes up the data plane. And then the control plane is a separate set of components that then interact with the data plane, interact with each of the proxies, and give it the routing rules that it needs, give it the timeouts, retries, settings that it needs, and overall manages the lifecycle of those rules as they change. So in Istio, there are three main components that make up the control plane. The first one is the pilot. The pilot is the main component that developers, operators will interact with. It provides an API for describing the configuration for controlling routing and security and observability and so on. So we can, Istio comes with a command line client. You probably more realistically going to interact with pilot through your CI/CD pipeline and automate a lot of these steps. You don't really want to be doing a lot of stuff by hand. The other side is pilot has an API that the proxies can understand. So the proxies are periodically calling pilot and asking, hey, what's my latest configuration? What should I be routing to when I talk to foo service? Is it V1, V2, or whatever? So the proxies are periodically checking with pilot to see what their configuration is. So that's kind of the main component for controlling the configuration of the data plane. The second component, also very important, handles a couple of different concerns. One, it handles policy. So how frequently can service A talk to service B, rate limiting type things, or quota management? Or can service A even talk to B? Service A is running in the public cloud. Service B is running on your on-prem. We don't want communication going that way. So with the mixer, the mixer component, we can describe policy configurations that now when requests are flowing through the data plane, the proxies are constantly checking with the mixer. Hey, is this allowed? Can I do this? And if so, what's my quota? The second thing that it does is it asynchronously reports back what is the telemetry, what is the tracing information, and that gets sent back to mixer, and the mixer has a pluggable adapter model that you can then shape that telemetry into whatever backend you use for metrics collection, Datadog, New Relic, Prometheus, or whatever. So Mixer provides a couple different functions and is a crucial part of the policy and observability implementation of Istio. The third main component is the Istio Auth component. And this component issues and rotates certificates to the different application workloads. And so what this means is so for example, X509 certificates are issued and managed into these different pods that the proxy can now use. So the proxy can use these certificates to encrypt the traffic transparently to the application. So we can get mutual TLS out of the box without having to mess around with Java key stores and trust stores and all that crap. Java, the Java app just uses what it thinks is plain HTTP, and the proxies secure the communication channel between the different services. So all together, this is kind of what it looks like. You have an edge ingress that could be an API management functionality, and traffic gets into your cluster. And once it's inside this cluster, Istio can enforce policy, secure the traffic, and enrich with reliability type things, and control the routing between the services. So let's go through these a little quick. I'm going to show you a demo. Enough talking here. This is retries, zone-aware load balancing, traffic control and routing. So we're gonna look at this in the demo. We're gonna look at we're gonna deploy a new version of our service, but we don't want to just big bang deploy it, right? We want to slowly release it by controlling traffic and how it gets there. Istio can also do traffic shadowing, which is also very crucial for being able to more safely do your deployments. So if you bring a new deployment into production, you don't, like I said, want to just open the floodgates. You want to slowly bring traffic over, but maybe even before that, maybe we could just sample the traffic that's happening in production and send it to our new deployment and see how it behaves without impacting any real production traffic. So we can do traffic shadowing, talked about the mutual TLS, some of the observability stuff. So in our demo, we're going to look at a very simple architecture, simple to understand architecture. It's based on the Istio tutorial that the Red Hat developer program put together. Pretty awesome tutorial. In this architecture, so a client will be talking to a customer service, and we see the customer service here. And the customer service will be reaching out to a preference service, and preference will be talking to the recommendation service. Now, this area right here is where we're going to inject and introduce new versions of the recommendation service and interesting behaviors that we can, reliability behaviors that we can make our microservices here more resilient. Yeah, so let's get going on that. But before I miss this last slide, reach out to me if you have any questions or if I said something that doesn't make any sense. And I put this up here. I've had people come up asking later, can I email you? Can I really reach out to you? And I was like, yeah, that's why I put this stuff up here. Email, Twitter, all my slides, this slide deck included is already on SlideShare. So let's look at the demo. So the first thing we're going to look at is, now this is a live demo. It's running on my laptop, but I always get people asking, are you really typing that fast? No, but it's a live demo. It's scripted, and could fail. But so we're looking at the architecture where we have a customer service, preference talks to recommendation. Right now we have recommendation v1, and if we look closely, we see that there are 2 out of 2 containers ready in each one of these Kubernetes pods. So we have the application itself, which are JVM applications, and the proxy co-deployed with the instance here. Now, on the bottom pane here, we're going to start sending traffic into this demo. We talk to the customer service, which does this call graph. What is this? The next thing we're going to do is we want to deploy version 2 of the recommendation service. So we want to do a deployment, but we don't want want that to take traffic, right? We don't want to just do a big bang release. If we look at this YAML here real quick, this is a basic Kubernetes deployment resource that describes the recommendation Docker image v2 of a recommendation service. But what we're going to do is we're going to inject the Istio sidecar, Envoy. So if I didn't make that clear, that Istio uses Envoy as the default service proxy. So what we're going to do is we're going to use Istio control and run it against that deployment YAML. Come back up here. Right, so we're going to do Istio control kube inject, and we'll give it that Kubernetes deployment YAML. And what it's going to do is enrich it with the sidecar container and then some other configurations that it needs. You can see that here. It's going to configure the proxy to talk to the Istio control plane and some other configurations, right? So we didn't actually install it. We did Istio control kube inject. It just spit out that YAML for us. So now we can install it. Let's do that. We do the kubectl apply. So we just created, or will have created, a new application v2 that is running in our Kubernetes cluster. And if we give it a second, did it come up? Yep. Now, using the default Kubernetes behavior, if you're unfamiliar with that, it should, I don't see it yet. It might take a second. I've seen this happen. It should load balance between V1 and V2 automatically, because Kubernetes doesn't, if the labels match on a set of pods, it doesn't differentiate which ones are which ones. It's still not load balancing. Well, just trust me, that's what the default Kubernetes behavior is supposed to be. Give it one more second. Nope. All right. Well, let's continue on with the demo. Hopefully that doesn't break anything else here. It is gonna break this part, but let's keep going. There's a couple other things that I can show you here. In this next step, what I'm doing is let's assume the demo worked and we saw V1 and V2 load balancing in there, because Kubernetes doesn't have that fine-grained control over what version is what version. In this next step, what I did was I created a Istio configuration to route 100% of the traffic to V1 of recommendations. Now, in the next step, what I'm going to do is route it to V2. So I'm going to use Istio, if everything works correctly, and I'm going to now explicitly split the traffic, V1 and V2, 50% for each of the different versions. So if we try that, cross fingers, on the bottom we should, once that configuration propagates, we should see it now split the traffic between V1 and V2. Now, obviously, we wouldn't have done 50-50. We would have done maybe 1% or a fraction of a percent and slowly move traffic over. But using Istio's configuration model, we can control how traffic comes into the services, and not just at the edge, right? So some of this basic routing stuff you can do with some of the API gateways, but we're talking deep into a service call graph. The next thing I'm going to show is, remind myself, I think it's retry. So the next thing we're going to do, the very first command that is getting run there is we're going to inject failures into our service calls. So that since Istio, the service proxy or Envoy, is sitting in between the traffic, we can do interesting things like chaos testing and injecting failures into the call paths. And what we did here was we purposefully injected 503s 50% of the time when we start to call the recommendation service. Now, just imagine for a minute that we didn't do that and that we are seeing network issues or application issues. The next thing we're going to do is create a route rule that introduces retry behavior. So if we do make a call and we do get 503s, we'll automatically retry. For a handful of service implementations, this is pretty handy, and you don't have to touch code to do this. For other calls where you're actually making changes to data in the back end and that kind of thing, you have to be a little bit more discerning about whether you want retries. But here we see the traffic went from 50% of the time having 503s to now it's back to sanity, right? If we see failures, we hide that and just retry automatically. Applications didn't touch anything on the application. Let's clean that up. We'll come back. We'll come back to that. Let's clean that up. So I deleted that. We should see the 503s come back. Maybe. Okay, 503s came back. Now we're going to delete the 503s. We don't want any failures in this next part. The next thing we're going to look at is when you do a deployment or make changes to your services, one of the nastiest problems is when you introduce latencies and unexpected slowness into the system. So if we do that in our next demo, we'll deploy an application, the V2 of the recommendation service, but this one actually has a delay hard-coded in it so that we can show it calls slow down. So if we come over here, we see the delay is up and running. Now on the bottom pane, what you should see is the traffic flows, go along, and then periodically it'll just stop and hang. I think the timeout was 3 seconds. So it'll just automatically, it'll stop and it'll hang, and we don't want that. When customers are going through, let's say, a checkout process or the shopping cart, whatever, we don't want these delays to propagate out to customers. So what we can do is introduce timeouts using Istio. So we're gonna create a new Istio configuration, and I'll show you what that looks like. Here's the timeout one. What that says is we're going to enforce a 1 second timeout. We introduce a 3 second delay into that new version. Using Istio, we're going to say anything over 1 second, we're going to time you out. And if we come down here, we should see that as traffic goes along, and we end up hitting that service that introduces the delay, which, there we go. After 1 second, it'll cut it off. Right, but we're still, our customers are still seeing this undesirable behavior, this 504 timeout. So we don't want that. The last thing we can do is, if we're getting bad behavior from certain endpoints as we load balance and direct traffic through the cluster, if we're getting bad behavior, why don't we employ a circuit breaker on that so that we can work around that. So what we're going to do here is create an Istio config that specifies circuit breaking policies, so that when we end up hitting one of those bad, or in this case slow, back ends, that will kick it out of the cluster for a period of time. 5 seconds, I think, is what it is. And here you see we're still getting the 504s periodically, but when we do, we kick them out, and then we see a long tail of no issues, right? And then as that endpoint gets brought back into the cluster, we'll see it again. But we don't want to see any errors, right? So what is one thing that we can do to smooth this traffic out even more? Anybody? Retries. So if we see that endpoint and it gets an error, we kick it out of the pool, let's retry on that call. So we don't have to throw back an error. Let's retry around that. So we create another route rule, Istio route rule, that will then perform retries when we get that 504. So what we've done is we've introduced, and you shouldn't see any errors in the call stack here. So what we've done is we've made our services even more resilient. We've done some fault and chaos testing of our services without touching any application code. Now these services happen to be written in Java, but they could have been any language, Node.js, Python, whatever. And I just showed you just the resilience, some of the resiliency aspects. If I come over here, I really should end this demo, but I didn't actually touch on the dashboards here, which should give, cross fingers, maybe? Nothing. Doesn't give anything, but it should. It should show traffic behavior and failures and so on. I'm not sure exactly why that's not working. It's a live demo. We got most of it to work. So we got 30 seconds left for questions. Anybody have a question? Yes, sir. Yeah, back there. Oh, you got a microphone.
Is Istio production ready?
So Istio we just released 0.8 a couple weeks ago, and that is intended to be a longer-term release. 1.0 is probably not coming until later this summer, and from my perspective, as someone who's been in the field, someone who's worked with customers and had a lot of responsibility on these types of projects, that I wouldn't put Istio into production just yet. It's getting there. Some of the performance issues, some of the security issues are being worked out, and it's getting there. The proxy, Envoy proxy, is battle hardened. I would say that is running in production at quite a big scale at quite a handful of customers or companies. But Istio's getting there. I would say kick the tires on it, explore its capabilities, juxtapose it to what you may have now, maybe with Netflix OSS, and be ready to move to it. But I would say in a little bit. I don't know, I'm probably over time here, but done? Okay. All right, well, I'll be around for a little bit after, and thank you so much for coming.